Özellikle de kompozit
and polymers, especially the intervals of fiber, is an area that I like and I'm curious about. By the way, I have made a consultancy of glass fiber in Aksa as well. I had worked together. I have worked together more than 40 companies. So on one hand, I am working in the academy. On one hand, I'm working in the industry as well. So I really enjoy my life in that manner. What I'm going to talk about today is actually quite a contemporary subject, and many of them are samples and examples from the literature. But finally, I have also some certain examples from my own research group at the end of my presentation. And yes, this is the title of my presentation, Intelligent Composites or Smart Composites. I prefer to use the intelligent terminology because we are expecting new things from the new features from the composites, and this is also one example of it. So since you are all here, you already know you already know better than me what a composite is. It's a high resistant fiber, a high module polymer, and there is also an interval here in between that is make of the fastening. And when we can take them all together, we say composite. But in Turkish, composite can be used for aluminium parts, for metals. But what we understand from composite is fiber. We all know fiber. We know carbon. We know glass, ceramides, and there are sophisticated ones as well, like boron. And then we have a high composite polymer, polyester, vinyl ester, epoxy. It can be thermoplastics, or polypropylene, polybutylene, etc. But they are actually structures that are not alike to each other. Some are organic non-polar polymer, and on one hand there is inorganic polar fiber, if we are talking about carbon and glass. So this is actually an interval here that connects each other. But that interval is actually making up this composite, of course. If the stress transfer in a material cannot access to a fiber, and the fiber's volume is actually 150 times more than the fiber. If we cannot put any load on a fiber, then your composite doesn't work at all. Then we have also, I have here my stick. I'm sorry, maybe it might work. These are particle composites, fibered composites, and there are also plates like nickel composites that are layered, like combined by plates with thin layers. These are all that we know. And then everywhere the composite, we have composites everywhere. So I have here wood here. It's a natural composite in lignin. It's a composite particle, and its actually behavior is like that. And actually, the composite that the nature is doing. So in our bodies, the skeleton, the femur bone here is a very strong and tough material, but is a composite. It comes up we have a protein matrix in the bone, the calcium salt, calcium apatite as well, which is actually it's a fiber which is made by the nature. This premise is actually a composite. We might not think that this is a composite, but it is a composite. It has the fiber, we have steel bars, but the mattress is cement. We are living in a composite building, and especially in this part of the area, especially we are deciding to use our medium is is to use actually these composites according to the earthquakes. And we have, of course, on the other side, concrete reinforced buildings, and we have speedboats, and we have also the wings of the planes. I have a contrabass picture. It's a wonderful contrabass. It's made of carbon fiber and better than actually the wood composite. On the other hand, I didn't believe it, but it is said so. The advantages must probably know it better than me. They are high. It is high resistant. In shrinking, it is very light. It is also very flexible. The design is very flexible. We can give out the Corvette car, for instance, can be an example for this. That the air, the AC area, for instance, in not every the sexy bands can only be done on a composite main body. And what I like about composite body is this actually. It can be so flexible because you could never think of a shape, of a form like that. So when we take a look to our civilization, let me talk a little bit about the philosophy as well. The human civilization is made of wood, stone, and metal. Take a look to our ancestors. It is what we found from nature. But now we can find also in plastics and composites. Apart from these natural resources, we have synthetics here. And on the other hand, there are new materials that is optimized for that business only and only, and we are doing it in the last 100 years only, not long enough, not longer. Give me a specification. According to the specification, let me do a plastic composite part or particle. For me, that's a wonderful success. Of course, the dimensional stability, the dielectric, the resistance, corrosion, resistance, these are all the things that you know. And there's a little bit, I just wanted to make an introduction, actually. We can give some more features, transparency, and we can say combustibility, especially. We can make it resistant to heat. We can embed metal inserts. We can combine it or connect it to another particle. We can actually repair it, we can actually drill it, cut it, and glue it together. The wing of A308 is totally glued. So just think about it when you once again enter into a plane. It is totally composite, the plane, and it is glued to each other, all the parts. So this is about, with a plane about 300 tons, and it has longevity about 25 years. But that's not enough, of course. Now we need something more than that. Now there is an intelligence inside it as well. What does that mean? In this composite, if we can put a sensor in this composite, it can perceive something with electronic materials. These sensors can be just the head of a needle. It's so small, it has become so small, like the head of a needle. It can perceive the load upon it. I have bent it as this much, if it can say. If it can only say and it can only give information about its own health, which is called the health monitoring in the composite technology. Or if we can give a signal from outside. Now I know the mechanic of this. I know how much it can bend. I can calculate it. But if with a single, can we change actually this module, this spanning module? The part is the old part. I'm not going to make an older one. This is what I mean about intelligence. To give information with sensor, with a signal that is given from the outside, we can change the mechanical features. And there are plenty of examples from that, and some of the examples are very simple but immensely successful. Let me give you some information and let me give some examples about this so that I can excite you.
tarihimizden bir akıllı örneği
let me
size
give you
göstermek
a smart and intelligent building coming from our history. It's somewhere that you know, in the Dolmabahçe Palace, in the harem chamber. This is in the entrance of a wall. It's in just the corner of the wall. There is a place that has been opened up, very nicely done. It's a green marmor, and there is a cylinder within it. It has been, the axis is wonderfully made. The diameter is just like that, with a length like that. Every day, somebody is coming that, and it is actually spinning that cylinder every day. If in the building, if there is no shifting, then the cylinder is spinning wonderfully. If there was an earthquake or happened something and the building has shifted, the parallelity of the distance between the pins is distracted, and the cylinder cannot spin. So actually our ancestors have given an information like this. I believe that I regard this as a very intellectual building, very primitive, but the philosophy is just the same as today's world. This information is giving, actually monitoring its own health, saying that I have shifted, I can collapse the other day. It says it's wonderfully made, really. And let me give you some information or examples. Yes, it's they are very simple technologies, and one of them is like that. Here we have this optic fiber quartz in a certain angle. After a certain angle, doesn't make a more axis. If there are, for instance, when we turn with a larger radius, because the inner refraction doesn't allow it to actually turn a corner at a certain radius. And that in that angle, to the composite part, we can embed an optic fiber optic. Both parts are taken out from each beginning. It is done during the manufacturing period, and it's going to stay there forever. And it stays there so that we can make a calculation in the future. Just one fiber optic, how cheap it can be. It's like only cents, but it should be actually embedded in a perfect angle. The test is done with an undestructive way. We need actually a light resource, a detector. When the part elongates, the fiber optics angle will change. And when that angle changes, when the angle gets larger, then the light diminishes. If you make this arrangement, and then at any time, this material, of course, we need to have a calibration tendency here. We need to make a part here so we can actually how much of this, we need to find out the calibration tendency just once. And after that, each time the part is smaller, the light is longer, the part is getting longer because it's under a load, and the light gets diminished. And with this change of the light, when you correlate the load on real time, it perfectly can we can perfectly calculate the load on the part. It's a very simple application, actually. And we have also, there's also the application of this as well. As you know, when the planes get on the ship, on the plane ship, there's a great pressure, and it's like a bomb. When they just land, there's a steering flow, there's a composite part here. I try to actually draw it like that. Of course, that part is a little bit more complicated than this, but it has been done. It's actually an application from grammar. During the manufacturing, the fiber optic has been embedded and is waited to be calculated. When you put a detector and also the light, then each time of landing, they can actually find out on what kind of an impact they are facing. You can calculate it as easily. You can actually record it as well. It's a wonderful training tool. So I made the graph a little bit more simple. I simplified the graph. The landing date, the normal landing, and but the impact was high on one. And once maybe we need to actually warn the pilot or train the pilot during landing. The part of this wheel's load should be actually calculated on real time. It's wonderful to do. And when you have to put a fiber optic inside while you are manufacturing that part, it's such a simple thing. And the data processing is actually way ahead for me, because the information that has been taken from that, how it is processed, I do not have a lot of information or knowledge about this. Please do not ask me then about it, but I understand the principle for it, because you need to actually calculate the light to process the data, and you can you have to main it, and you have to make it usable and applicable. And let me take you Rumkov pulley. 200 years ago. It was made in 1865. It's a very simple principle of physics. It's a pulley, and that magnet, when you move the magnet inside the pulley, then you create a potential, and you can calculate that voltage. There are plenty of applications like that. The electricity generator's principle is this. It has already been known for centuries. So if the previous example is the static, it is calculating the static load, but the Rumkov modules, so that it can actually create a voltage, then you have to need of a movement. You have the need of a movement. A static tendency doesn't answer that or respond to that. You need a movement. The magnet should move inside the pulley, like you need to have a vibration. And vibration is part of our lives. A vehicle, a bridge, a structure cannot live without any vibration. In one part of his life is going to live that vibration, and they're trying to calculate that. And in Kyoto, Kyoto is also an earthquake region. There is a bridge with composite parts. There's an application for that. This is a very simple application, but my drawing, of course, is not showing this quite well, but there was a pulley here, a small magnet put on and connected to alnico permanent magnet of plate, and 1 centimeter, smaller than a stamp. It's just smaller than a stamp, that part, on size. You are going to embed it during manufacturing the composite. And the position, it's not the position of the magnet that creates the voltage. The speed of the magnet is what's important. For instance, in an iron structure, the iron has actually, due to heat differences, it's not actually reading the longering or shrinking of day and night temperature differences. When the voltage is moving, that voltage is going to be processed. What's important here that what the operator sees, that the vibration of the bridge coming from the data coming from that part, the operator has to see it on real time. In normal days, the vibrations of the bridges and the vibrations during a stormy day, that really was in the actually graph. Of course, that's outside the scala, but the construction was very tough and rigid. But the composite part you could see on real time what happened to that bridge with a very simple and cheap structure. And the part is going to be manufactured and going to live there its whole longevity. It's a very successful application. The ultrasound acoustic examination has already been known for years. And one of the first examinations that we have known so far, there are two parts of this: the sound resources, the sound detector from the other side of the parts, and then we have on the same instrument you have the sound source and the sound detector, and then it is reflected, and you get that information after it. Let's say that you go to a doctor, the medical treatments of ultrasound has already been known. You can see any kind of a detail of a baby and the womb. In general, the resolution of this smallest part that is seen is actually depending on the wave size of sound. So when you longer this frequency, then you get the so for instance, it's at about 60 hertz. It's at 60,000 hertz. It's higher than our hearing limit, so that's the reason why we cannot hear what's coming out of that sound. But they say that the dogs are hearing it, but we cannot. And it's a known technique, but let me tell you, this acoustic examination has a limitation. When the part gets thicker, from the upper sides to downside, all the reflections coming from the lower sides is coming to the detector at the same time. That's the reason why it's not very successful in thicker parts. So we want to see if there is a delimitation. If there is a gap, is there a rich part of raisins or fiber? Because we want to see inside of the structure. The sizes are very small, and that's the reason why you need to have a device that has high frequency. And it's also important where this problem occurs and how deep, not only where it is. These can only work with thin composite particles. They have worked on it, actually. Technically, there's not much of a difference. Let me show you how much difference they have made in the technique of doing this. They are calling it active acoustic examination. Just one simple difference here is that is actually we embedded the sound source to the part. That's the reason why we don't need to have the set source. That part is again been embedded inside the part during manufacturing, and it's going to live there throughout its longevity. And these are piezoelectrics. It's going to give the sound anytime you want to, and it becomes a very simple examination. It's a detector that you can use by hand, and you can actually examine the whole part of the parts. And it's drawing it, and to make it to a picture. The signal process is not very easy, and for me it's not at all easy, but the application is easier. So the Airbus 350 prototype has been on the parts have been already been done, and they are more installed together. And all the parts that have been installed, they are small. So this is a small detail here that you can see on the picture. The acoustic sources are put inside the composite parts, and that connecting the bounding parts, the delimitation, is not wanted, of course, and that is the reason why there is an active acoustic examination method that has been developed. Why is that so important? It is because the sound is coming inside from the part, and electronically the harm parts, we can get an idea on how much harm and how deep that harm has been occurred. And in the previous method, it was not possible for us to get that information.
hoparlörlerden bahsettik.
Piezoelectric sensors, for instance. The Berlinite, most probably it's been years, for 100 years, most probably there's some very small stamp. Piezoelectric censored composites and devices are widely been found. Of course, more larger piezoelectrics have been rather much more been seen. This is this 8 centimeter like longevity. It's made of quartz. Quartz is more sensitive, but to make it small and flexible is not possible. Berlinite is smaller and is very flexible, and that's the reason why the Berlinite piezoelectric crystal detectors are much more been preferred. And what's the important point of this? So during an impact or during a vibration, it produces a potential. And the potential that is produced, and the flow and also the amplitude depends on the strength of the amplitude of that impact. Let's see how they are using it. This is also a field that I like. This is Alingni. A sailing boat, American Cup, a sailing boat, it's a Swiss boat. I suppose it has won the cup 4 years ago. It has actually an epoxy carbon rudder frame. The angle of the rudder frame is very much important because we wanted it actually spins the boat. But the laminar flow and the boat's speed is not slowed down. It's slowed down only in a minimum way. It's a speed sailboat, so you need to actually win that cup. And every kind of technical development has been implemented. The laminar flow converts to turbulent flow. You need to have a really big. It's going to have a friction here. It's very much important for the person on the wheel. There should be no frictions. The composite rudder, piezoelectric sensors have been put. The pure turbulence is creating the water movement, and the former, you can understand it also because you have a vibration. You are when you are holding the wheel. It's giving it's responding perfectly. The person who's on the steering wheel saying that you're slow downing now. It's very simple and very perfect to use. It's very important for the person on the steer wheel saying that you get a message from here, you're inside a turbulent flow. Very simple implementation. On the outer skin, you can put it on the outer skin and embed it on the structure. Well, another sample. RFID most probably is in everywhere. Also in our country, HGGS, for instance, is also valid. In my car, it is censoring the number of the license. It's actually scanned and read. It's been used in many areas, in many fields. Fraunhofer and Mercedes had a project together. It's so simple. And when I read it, I said, oh my God, why didn't I think it before? A carbon fiber composite has actually a sealing of the car. And when that sealing is a composite on the car, then you have some opportunities that you cannot do with metal. the composite on the composite ceiling, it's necessary right now for a car, and all of them, AM, FM antenna, radio antenna, it's been also already embedded, installed. Many cars have a GPS antenna, Bluetooth or 3G antenna, RFID, vehicle recognition chip when you pass through a ditch or through a bridge, or when your car has been stolen, just like as you know in a chassis number, like a motor and engine number. So it can be put into this composite particle. Just think of this, there is no antenna on the outside of the car, and during the installation of in the factory, all the people working in that staff can also write down their numbers as well, saying that who this car has been produced by. It's very clever. And the part is very simple here. It's just been put, I do not know how you can see it on the window. There is a banded area just next to the window. It can be put inside it. Of course, it's not possible to do this in a metal part. In a metal part, RFID is not transparent. It's only transparent in specific situation. That's the reason why you need to have a good composite material here. Of course, think about the cost. There's going to be an antenna. Somebody will come and harm it. It's going to bend it, for instance. You take your car to washing, and then the antenna will go. No, it has no antenna. It's all embedded and inserted inside the car. Carbon or glass. In such a composite, you can actually have some advantages. All the radar domes has to be composites. You cannot do it metal. Microwave is not transparent. It's a wonderful application, and it's such simple. Another example I told you before, putting a sensor is one way to do it, and changing the features of the part is another application. People do that too. Let me just, would you allow me to take off my jacket? It's been quite warm inside. Again, it's an invention, the Bingham liquid, which has been invented by an Englishman. A viscose material, like gel. Think about a gel-like thing, a polymeric gel in general. And small whiskers. Whiskers can be put inside it. These are very thin magnetic ions. Think that we are putting a very thin fiber. Two sides electrodes. If there's no flow from a voltage source, there's no electrical field, there's no orientation. The electrodes are actually the orientations is actually done in not an ordered way. But if you put here something here inside, you can orient it. All of them are going to the same place, and it's a very well-known application. In electron microscopy, it is also possible to take pictures of this. When the circuit is open, the whiskers are randomly been scattered around, but when the circuit is closed, I don't know if the picture can show it, but there is an orientation here on the part. When there is an orientation, of course, these particles are behaving like an actual reinforcement, and that actually can strengthen the reinforcement. When all the particles are scattered, the resistance is lower, but when they are oriented, the mechanical resistance is stronger and rigid. It can be done by a source outside. It's been actually invented 50 years ago. Now, how can we put this as a composite application? Hughes has such actually an application. There's a problem, like a helicopter, Apache. We know that too. We have the pedal here. The deflection momentum is connected to the tour and the pedal speeds, and you have to optimize it as well. We prepare a part, and it's a titanium inserted part here, very complex. And while producing this pedal, the propeller, you can do it optimize up to a certain orientation here. When some helicopters are flying, apart from their normal voice, you have this pop pop pop pop sound. This is cavitation. The propeller is cavitating. It's in such a wrong. At the moment, it is turning and spinning in such a wrong angle that there's a vacuum here, that air that is collected that brings us up a sound like this, and the helicopter is vibrated quite a lot. It's not comfortable for the people inside and also for the mechanism inside the helicopter. As of course during war it gives also it localizes you to the enemy where you are. So this is an application right now. This is a paddle of the helicopter. Excuse me for my drawing, but I'm talking about this long paddle here. Inside you can put here the Bingham materials, and all of the voltage sources is coming to the axis, and we can do whatever we want to do with it. We can energize it, and just at that point, simply just at that time, you can change the module. So I can change long of this part the way we want it. I'm not talking about to take it 5 to 500. It's a very fine tuning. The Binghams that are inserted here can be mechanically we can change the mechanical resistance here. You can get a lesser propeller sound, the vibration decreases. Bingham materials were used under rover vehicles. The electrical this is actually a modification here that the Englishmen have done. But with intervention from outside, in any part of the part, you can change the deflection module, and you can finely tune it. If you can do this, it's a wonderful ability. Because you cannot always actually, if it's a low circuit that's not good, you need to have the ability to make the fine-tuning during flying. I love it, and that's the reason why when I see such things, I feel very happy. But I didn't do that perhaps, but it still gives me joy. A simpler application. Perhaps you have seen this double metal part in the elementary school. You're on the candle. Your teacher has heated up actually the metal on the candles, and you can see how the metal has bended. I have seen it. The nickel and iron. The thermal coefficients are different on the thermal way. Of course, there will be a bending. There's no other way to do it. Can we get use of this? It's a movement. When we change the heat, it's going to do this behavior. That part cannot be distracted. The thermal amplitude cannot change. Puma has a wonderful pike like that.
çıktı. Yanılmıyorsam.
And it has been in 2002, as far as I can remember,
çok başarılı
has
oldu.
been in the market, was very successful, and then it has been actually forbidden
Atletizm
by the athleticism federations. Let me show you what they did. This is a pig. Inside the pig,
bu sefer
this time they have a double metal particles and a resistance. When you heat it up locally, because here it's nice to show you, when you just push throw the pike as it goes, the strength of the athlete, according to the it is go in vibration. It is such a movement when the athlete is actually throwing it away. Of course, this is an energy loss. And if you can arrange it in a kinetic way, then it can go even further. So in each part, in that deflection, the flex, if we can actually arrange this flex resistance, then it can actually, we can minimize the vibration here. And then we have this double metal parts inside here, as you can see, which is giving a pre-tension here. When it wants to go, as you know, in cement, there's a pre-stressed part resistance is the increase, and then locally, wherever you want to do it, that's important, where you wish it to be. You can change the momentum of deflection, and with something that I give from outside. The pig goes further, and then you have a champion, and you got the golden medal, but it's later on been forbidden by the federation. It's as far as we can see, you cannot do everything in sports, but success is nice. And and there are also some shape memory alloys. These are things that we already know. For instance, nickel titanium is one of them. But now we have more sophisticated transition elements, and they're doing wonderful things. The principle is so simple. So you are a metal alloy has been molded. In this geometry, we pour it, take out of the mold, but later on, with cold forming, it was banded, but we opened this up, the form has changed, and it's now straight. So this is actually the memory of the form. If we reheat it, it will return to its former form. This crystal structure of this alloy can remember somehow the previous form. Cold forming has when it's heated, it becomes more comfortable. It comes up to its former form. It remembers it. So when you put this in a composite, it's coming here, and I'm sure you're seeing this as well. I'm going to put it in the composite, I'm going to heat it, and the composite is going to change its structure, its form. You have this material here, and stent, medical stents. It's done by, it's a texture made by a material that has a memory in form. Polyamide mattress. Polyamide is wonderful for the human body because the proteins are looking alike. Amide functionality is also available there. It's been accepted by the body. That's the reason why we use polyamide, and 666 has been used. Polyamide mattress is a form that actually remembers the texture here, remembers its form. We are making a form here, taken out of the mold. A very small cylinder, 3 millimeters to 7 millimeters. This is what the material is going to remember. Whatever we do to it, when it's heated up, it will remember this form. With cooling, they change actually the form. They elongate it. They do composite as well.
Fakat ondan sonra
However,
ısıttığımız zaman
when we
eski
reheat
şekline
it,
geri geliyor.
it returns to its
Stand işi zor.
former
Stand'i
form.
zaten tıkalı
Stand
olan
is hard.
hiçbirimizin
Stand
başına
is
gelmesin.
generally been used in a
Stand'i
vein
zaten tıkalı olan bir yere
that
götürmüşsünüz.
you have to put it
Nasıl
into a
tutacaksınız?
vein that has already
Orası
been
çok
stuck.
dar,
How are you
normal
going to do this?
damardan
It's
belki
very,
5'te
very
inç
narrow,
Onun için çok ince
narrower
bir
than a
hal.
normal vein.
Çekilmiş ve incelmiş
So it has to be
halde
elongated
ancak
and
damarın
flexed
o
and
bölgesine, tıkalı bölgesine
put
sokabiliyoruz.
inside
Ondan
this
sonra
part
çok
of the
kolay
vein
bir
which is
şekilde
stuck.
bir
And easily
uç değiştiriyorlar.
they are
Lokal olarak
changing
burayı
the
sıktıklarında stent
the
kesici
extreme
yapına
part here.
gidiyor, damarı
When they heat
genişletiyor.
it, the stent, when the stent is heated,
sağlıyoruz ve bu
then it
parça
remembers again the
metalle
former
gelmesini
former shape of it,
nikel
and then
peteş bir metal
that
değil
area
insan vücudu
gets
için.
larger. Nickel, for
Dışı
instance, nickel is not very
poliyamid
nice for the
kaplı,
human
ondan
body,
dolayı
but there
buna
is a
kompozit
polyamid
diyoruz. Elyafı
body just
metal,
over the
matrixi
material
poliyamid olan bir
here,
kompozit
and
ve hayat kurtarıyor.
it saves lives.
Yani başka bir kelimesi yok bunun.
There's no other way to
Nezle
say
değil,
it.
grip değil.
It's not a flu.
Hayat kurtarıyor.
It's just saving lives. Hardcore DuPont, how many years ago it was that I had the opportunity to go there. They have to make it a presentation. It's something that they do not like to actually speak too much about, but it's self-healing composite. It's a very fashioned subject in hardcore. In many magazines and many articles, there have been plenty of publishments that have been that has been actually published, and it's not anymore hidden. It's a solution in a very small capsule. Here, the size here is 6-7 millimeters. A very little capsule, a small capsule. But it has a very sophisticated filling technique. Epoxy and a cured epoxy material is put inside the same capsule with a very thin membrane. It has been separated. I have a capsule, half of it has epoxy and the half of it is diamine, the cured material of epoxy. Since the membrane is there inside, they cannot actually mix together, and they were going to stay there forever in the capsule up until something will happen on that capsule. The whole part will be bended up until the membrane has been fractured. Let me show you. So when the part has been actually broken, when we say repairing it, it's not the aim actually to take the part to the former module. So it's like that you have a wheel that has been exploded, but there is a part here up until you go to a station where you can change your wheel, but that is not forever, but so that the train can go, so that the car can go to the garage. I'm talking about the repair so much. Let's not expect more than that. And they have taken photos of this fractures, of these cracks. When the capsule is broken, the membrane is broken as well. They get out of the capsule, and in most of the cracked parts, epoxy and epoxy material is mixed, and in 3 minutes the epoxy is cured. It has low viscosity, and that's the reason why. It is wetting the material and filling it, so it is a part that actually reheals itself or repairs itself. The mechanical resistance are, of course, lower than its original parts, but it helps to work for a while. And I suppose this is the last sample for that of my presentation. Thank you very much for your patience. Gökhan, together with Gökhan, a doctorate student of mine, this is an article that we have published. Let me give you an example for this, and then I'm going to close my presentation. Materials that changes phase. A phase change, like solid to the physical principles.
sıvıya geçerken veya bir
to
sıvı
be
katıya
liquid
geçerken
and
bir erime
to,
entalpisi veriliyor veya
of course,
alınıyor.
when we talk about the change of phases, the solid goes to liquid, etc. And there's an energy exchange here in between.
Bu işi yapacak
So,
bir malzeme
a material,
doldurulmuş
it's
küçük
a material has been put.
borucuklar.
The small, we have produced
30
small
milimetre, 20
pipes
milimetre,
here,
aslında bunların
30
hepsinin boyu aynı değil.
millimeters,
Ben
etc.
30
But
dedim burada. İncecik,
the
çok ince
very
duvarlı
thin,
tek boru.
very
Delaware'de
thin
bir,
PET
firmadan
pipes here.
bulduk
We
bunları.
found it from a
İçlerine
certain
bir
company.
faz değiştirecek
We have
malzeme.
put a
İstediğiniz
material that can
sıcaklıkta
change
bu faz
phases,
değişikliği 50
and at
derece
any time,
civarında olsun
we wanted to have a
Söyleyeceğim
temperature of
Bir sürü
50
şeyler
degrees. I'm
denedik,
going to talk
parafin,
about the
peg esterleri,
structure here. We use
peg,
paraffin, PEG
naftalot
esters,
esterleri,
naphthalate esters, stearic acids, etc.
malzemeler denedik. Tabii,
We use
şimdi
plenty of
bu
materials,
erimeden
and due to this
katılaşmadan
melting or due
çıkacak
to
enerjiyi
this solidifying,
istiyoruz.
we
Onun
want
için
to
erime
have the
entalpisi
energy that comes
yüksek
out of
bir
this. That
malzeme
is the
arıyoruz.
reason why we are
Bunun
looking
için bu
for
malzemenin mümkün
a
olduğu
material
kadar
that is
kristalin
high
olması lazım.
in
Kristallerin
resistance
erime
here. That we
enerjisi
are
daha
looking
yüksek.
for
Ama
resistance.
oklarınki daha düşük. Onun için
Crystals.
birçok
A
malzeme
more,
denedik.
we used many
Bu
materials.
kapsülleri
And
çok
within
basit
these
bir
capsules,
doymamış
there's
polyester bir kalıp yaptık, bir kompozit yaptık.
unsaturated.
Şimdi
We have
kompozitimize
made
bakalım.
a composite here with
Matrixli
unsaturated
polyester,
materials.
İçinde
And
elyaf olarak
in fiber, there's fiber
bir şey var.
inside
Fakat
it.
o elyafın içinde de
But within this fiber,
erime derecesi 50 derece olan
there's
bir
also
malzeme.
material which can melt at 50
Tabii
degrees.
dışarıdan bu malzemeler
From outside, of
gözükmüyor.
course, you
Elyaf
cannot
değil,
see these materials.
kompozitin içinde.
It's just like a fiber that is inside the composite.
Bu ısı değişikliği
And
belki bir
this
şekilde
change of temperature
bir ısı depolama
can
metodu olarak kullanabilir
can I use it
Evet,
as
evet.
actually
Tabii,
heating
gayet iyi
storage
Düşünün,
material,
bunu ben
and it's
ısıttığım
working
zaman
well.
bütün 50
When I
derecenin
heat
üstüne
this,
çıkarttığım zaman
when it's
bütün
more than
kapsüllerdeki
50
malzeme
degrees, all the
sıvı olur.
materials in these capsules will
Sonra bu
be
parçayı
liquid.
bıraksam
And
yavaş
when I
yavaş
leave that
soğumaya,
material for cooling,
geri 50 dereceye geldiği
and
zaman
when
bütün
it comes to
malzemeler
50
katıya
degrees, all the
geçerken
materials
entalpi
go
enerjisi dışarı
solid, and the n-type
Yani benim
energy
biraz
will go
evvel
out.
koymuş olduğum entalpi enerjisini
So
ona
the
geri
enthalpy
veriyor.
energy will be delivered here.
Isı pili gibi bir şey.
It's like a
Şarj
heating
ediyorum,
battery. You
sonra geri
charge it
alıyorum.
and then you take it
İşte bunu
back.
yapmaya çalışıyorum.
So that's what we're trying to do here.
Nitekim
And
tamamen öyle
however,
oluyor.
it happens to be like that actually,
Malzemeyi
because
ısıtmaya başlıyorum.
I'm starting to heat the
50
material
derecede
at
ben
50
eridim.
degrees. It says that I melted.
Diferansiyel,
The
taramalı
differential
kalorimetre.
the differential
Burada bir
calorimeter says that there is
endoterm
an
var. Bu
endotherm
malzeme
here.
eridi diyor.
This material is
Ama mekanik
melted.
parametrelerine
But
bakın,
when I take a
çok
look to the
küçük
mechanical
bir
resistances
yumuşama
here,
var.
there's a very
Parça ben
small,
eridim demiyor.
it's
Parçanın
small
görünüşünde,
melting, but it's not
mekaniğinde bir
totally
fark yok.
melted because
Termal
the
olarak
part
eridi,
is
fakat
not
mekanik
changed.
olarak
Thermally,
eridi.
it has been melted, but mechanically it didn't melt.
Böyle bir malzeme yoktu.
There was no such a material.
Termal olarak bakarsam
Previously,
eridim
thermally,
der.
yes, it says that
Sonuçta
I
kadar
have
enerji
melted,
aldım.
so I have received so
Ama
much
mekanik
energy,
olarak
but mechanically,
mekanikleri değişti.
the mechanics didn't
Böyle bir
change.
malzeme ne işe yarar?
So what's it used for?
Bundan tabak yap.
How we have made actually a
hastane
plate for
isim
this.
vermeyeceğim.
A hospital,
Şikayetleri
not going to give the name,
yemek
and they had
mutfaktan
complaints.
hastalara gidene kadar
The
soğuyor.
the dishes cool
Tabağımız,
up until
tabağımızın
the dishes
kesiti,
go to
fazla
the
içtiğimiz
patients.
kapsüller içinde.
So we have
Tabak
here the
60
plate.
derecede ısıtılıyor,
The
içine de
plate
yemek
has been
konuyor.
heated up to 60
Ve
degrees, and they are put
arabalarla
the
dördüncü kat,
material and
beşinci
food
kat
is put
gezerken
inside. And when the
yemek de tabakta
car,
soğuyor. 50
of
dereceye
course,
geldiğinde içindeki
the
sıvılar
dishes cool
katılaşıyor.
here, and the liquids do get
Yemek
solid
soğudukça
here.
tabak ona ısı
But
veriyor.
the plate is giving heat to it.
Arkadaşım
It's
önerdi,
very simple.
pizzacılarla anlaşmamızı
He's told me to actually get arranged with the pizza stores.
ısıyı
The heat
depolayan,
is being stored
eriyerek ısıyı
by
depolayan
melting,
ve sonra da
and then
kontrollü bir sıcaklıkta
in the controlled
tekrar
temperature, it
depolayarak
can get
ısıyı geri veren çok
solidified
basit
and
bir
can
tabak.
give the
Tabii
heat
polyester
back
gıda
to the
temasına uygun
plate.
olmadığı
Of course,
için bu
polyester
tabak çok
is
başarılı değil.
not.
Kimse bu tabaktan yiyemez.
Nobody can eat
Polyester
from
uygun
that
bir
from that
tekstil
plate
iş
because
için
polyester is
daha
not a
iyisini
good
bulmak
mattress. We need
lazım.
to find a better one better material for that. And we are talking about food, I suppose. We are very, it's time, I guess, for lunch right now, and that's the reason why. Bon appétit. Thank you very much for your patience.